Good evening, students. So today we are going to discuss about the Zener block oscillation. We can ask one question: what is a Zener block oscillation? Then next question: how you can see it by the equation. So first thing we want to discuss what is in general in the Zener block oscillation. Suppose if you are having the any material having the periodic potential, whether it is metal or semiconductor or some quantum dot or quantum well structures, if you are having this kind of material, it will the electron moving inside the material, it will experience the periodic potential that is given by the positive charge ion inside the material. Suppose whenever the electron is moving inside, so it will experience the kind of the oscillative potential. Suppose if you are giving the external electric field to this material, that means the force experienced by the electron, if you are consider it is uniform. That is, we are giving the uniform external electric field. What would happen? The electron motion will be oscillatory inside the material. We are thinking whenever the constant electric field, if you are giving to the material, then the electron movement will be uniform, but it is not actual in the case of the semiconducting material or any material. The electron motion in the uniform electric field, it would be oscillating. That oscillation we can call it is a Zener block oscillation. This is a Zener block oscillation. So the simple definition for the Zener block oscillation is when an electron is moving in the uniform periodic potential. Uh, One second, I am sending the pointer. So when an electron in a periodic potential acted upon by the constant external force, that means constant external field, the motion of the electron would be oscillatory instead of the uniform motion. This is called the Zener block oscillation. Now we will see how you can derive the Zener block oscillation using the classical model. Today we are not going to derive the quantum mechanical expression for the Zener block oscillation. It's just a simple the classical model. Then we can see it in animation.
So, when an electron is moving in a constant electric field, the force experienced by the electron F equal to minus the charge of the electron times the external electric field. Suppose if the electric field this direction, the electron movement would be opposite to the external electric field. So the force is nothing but it's a derivative of the linear momentum that should be equal to E times E. From the de Broglie relation, we know the momentum of the electron is equal to the h cut times the wave vector k. So this is a given momentum of the electron, d by dt, the p if you are substituting from that expression, h cut k is equal to minus e time e. H cut is a reduced Planck constant. It is a constant. You can take it from the derivative. So if you keep it outside, it's dk by dt minus e time e divided by h cut. Then if you are rearranging this equation, it's a dk equal to minus e times the h cut times dt. If you want to know the momentum of the electron at any time t, just you need to take the integrate on, or you have to take the integration on the both sides. Suppose if you are integrating from here also you have to take the integration. At the starting time you can call it's a t. At the measurement time, the moment of the wave vector of the electron at time t, we are going to measure the initial momentum. You can call it's a zero, or the wave vector initially you can simply call the electron is at time t equal to 0. Then final wave vector you can call it's k. Suppose if you are integrating left hand side, it will give k at a time t. The right hand side of the equation, electric field is uniform constant, charge of the electron is constant, h cut also constant. You can take everything outside. If you are integrating this one, it will give simplicity. This is the wave vector of the electron whenever it is moving in the constant electric field. Suppose if the electron is moving in the periodic potential, then the energy relation we got to put in the semiconductor. Suppose if the electron is in semiconductor, we are going to use the energy dispersion relation versus wave vector. Right now, what is the group velocity of the electron? Because we can't put that inside the crystal, the velocity of the electron, the phase velocity of the electron, because it will experience the different field inside the metal. So you can define what is the group velocity of the electron. That should be equal to Vg. It's simply d by uh, uh, dp, I think. So yes, so we know the d, the p is h cut k. You can take the h cut outside. It's h cut time dk, because h cut is a constant. So 1 by h cut d by dk. This is the group velocity of the electron whenever it is moving inside the crystal. Now we know that energy dispersion relation E of k, that should be equal to some amplitude times cos a k, or you can take the sign a k. It's from the tight binding model. It's from tight binding model. What is the energy dispersion relation of the electron inside the crystal? A is the lattice parameter. Capital A is represents some amplitude. Here k represents the wave vector of the electron. Now we got to substitute in the equation the k value. Then your E of k is equal to a time cos a minus e t by h cut, or else you can write a time cos of minus theta cos theta simply. So charge of the electron, the lattice parameter, the external electric field divided by reduced Planck constant time, the variable t. This is the energy dispersion relation of the electron inside the semiconducting material or inside the material. Now our aim, we want to calculate what is the velocity of the position variation of the electron inside the material. So how we got to do? We know already that the HR derivation. The once we know velocity is equal to dx by dt, the rate of change of the position, we can call it the velocity. So here what we know, that the group velocity of the electron, because it's not a phase velocity, that already we derived, the group velocity is equal to 1 divided by h cut de by dk. This is the group velocity of the electron. We know from this equation what is the energy dispersion relation. We want to just you have to substitute that energy dispersion relation here. Then if you are integrating on both sides, we will get what is the position at any time inside the material, the electron. We can define the exact position of the electron inside the material. So the velocity of the electron be equal to dx by dt. This is equal to 1 by h cut d by dk. The energy dispersion relation, we just now derived that value for the energy dispersion relation. That is simply a, the amplitude times the cos, the lattice parameter, the charge of the electron, the E divided by h cut times t. So this is the energy dispersion relation, or you can call simply, because right now we don't want the variable t, you can call this is equal to the k. That means the charge of the electron time electric field time divided by h cut, that is equal to k, because here the derivative is dk. That's why you got to write the velocity, that should be equal to 1 by h cut d by dk of a cos ka. If you are differentiating this one, you will get, because if you are differentiating the cos k, it will give sine minus sine, so minus sine the sine ka, then it will give the if you are differentiating that argument, it will give the a outside. You can write it simply here. This is equal to the dx by dt. Now you can substitute the k value, the wave vector of the electron, that is A divided by h cut sine of, we know what is the k value, it's a E divided by h cut times t into lattice parameter. You can just put it here, the lattice parameter, this time the dt. Now because this dt I'm just pushing to the right hand side. Now take the integration on both sides. You can just initial times, the starting time of the electron is 0, the ending time is t. The starting position you can take either x0 or 0, that is our wish. Then the end position is at x of t. Suppose if you are integrating to the left hand side, it will give x of t minus x of 0, that should be equal to, if you are integrating right hand side, this is constant a divided by h cut. If you are integrating sine, it will give minus cos, then that argument a divided by h cut times t. Then you need to substitute a divided by the coefficient of the t in the denominator, 0 to t. So it will be equal to, even you can cancel this one, this one, this a, then you will get a divided by e times e. Here it's a sine function. If you are differentiating it, cos, minus into minus plus, if you are substituting this earlier, it will give cos a e divided by h cut times t minus the cos 0, it is 1, so this will be the side. This is, you can call x of t minus x of 0. Now the final expression of the x of t, that should be equal to the x of 0. If you are observing this constant 1 times, if you are here minus 1 time, this constant also inside the initial at time t equal to 0, the position is constant. If you are observing inside it, then it will give a times the cos of a h cut times t. So this is the position of the electron inside the material at any time t. It is varying as a function of cos. That means that this expression shows that the electron oscillate in the real space. That means the position of the electron is varying. Here we are not, we didn't solve the any Schrödinger equation, just we are using the classical expression, just we derived the position of the electron at any time t inside the metal when the external electric field is acting on it. So this will give the some kind of oscillation. The period of oscillation, from here you can just guess it. The period of oscillation is the omega b, you can call, that is the lattice parameter time the charge of the electron time the external electric field divided by h cut. If you are increasing the external electric field, then oscillation frequency will increase. Suppose if your lattice constant will be large, then oscillation frequency will be large. Then E, h cut are constants. So this is the expression we can, from the classical expression we know that electron is oscillating inside the metal whenever the electric field is E is given. This kind of oscillation we can call it a Zener block oscillation.
Here you can see the pulse. This pulse represents the electron wave function. If it is moving, this is a periodic potential. It is showing here in the red up and down curve. So if it is moving inside, the pulse is moving inside the periodic potential. That means the electron movement. It will be oscillating. You can see the electron is moving to the right end, and then again it will reflect back from the end. Then again it will be moving to the left end. So it is showing kind of oscillation. This oscillation we can call it a Zener block oscillation. This picture is taken from the Wikipedia. It is a like just animation picture how the Zener block oscillation is looking like inside the material. So that's all we want to know from the theory, the Zener block oscillation. Here you can see the pulse, it's moving to the right plane. Then after that, it is getting reflected back to the left plane. So this kind of oscillation is called the Zener block oscillation. Here it's just a simple definition for the structure. Pulse interacting with the periodic structure with the superimposed gradient in the refractor showing the block oscillation, because the inside the material it is experience refractive index also. That means its frequency will change, but it will experience the velocity delay. That is, we can call the refractive index. So they included the refractive index also, and they have shown the how the pulse is oscillating. So this is we want to know. So from today lectures, just we first saw the what is the definition for the Zener block oscillation. In the next slide, we saw the derivation, the simple classical derivation. The end slide, we have shown how we can visualize the Zener block oscillation using this animation. So that's it.